Come on, my dears, let us proceed further in chapter number 7. Today, most probably, we will finish this chapter. Okay? Let us see now this article. Use of transistor as a switch. Normally, what happens if you have switch in a circuit and then if it is in a working condition and if you switch it off, then the circuit stops working and it is already in off condition, and when you switch it on, correct, when you change the condition of the switch, then if previously circuit is in off condition, now it comes in on condition. So switch is that electrical component which changes the condition of output voltage, correct. Normally, when you switch on any circuit, we get output voltage, and when you switch it off, we do not get any output voltage, correct. But here in case of transistor, it so happens when you switch it on, at that time we do not get output voltage. When you switch it off, then we get output voltage. So it also acts like a switch, but better we should say it acts like a reverse switch. It acts like a reverse switch, because when we switch it on, it does not give any output voltage. When we make it switch off, then it gives output voltage. So you can say transistor acts like a reverse switch. Then you may have a question, how? Correct? I am showing you. Here is transistor symbol, and because I have shown this arrow outward, it must be NPN transistor. This is collector, this is base, this is emitter. Fine. And I have joined it in a mode which is called common emitter, because this is input part of the circuit, this is output part. In both, emitter is common, so we call it common emitter, correct? Fine. With base, the resistance connected is RB, and with a collector, this resistance connected is a load resistance RL. Through input voltage, we will supply necessary forward bias voltage, and through this battery, which is VCC, we are supplying reverse voltage in the output. Okay? Through this voltage, we supply necessary input forward bias voltage, and through this battery, we are supplying necessary reverse voltage. Come on. Now this terminal I am taking positive, this terminal I am taking negative, because I need to make this input junction forward bias, because it is NPN transistor. Here it is P type semiconductor, to which I must give positive potential. Okay? Fine. The current passing through this resistance I am taking as IB, because it is passing through base. Potential difference between base and emitter I am taking VBE. Potential difference between collector and emitter I am taking VCE. Okay? In textbook, in this article, they have taken this as output voltage VO. Okay? Now tell me, in the input part, if you apply Kirchhoff's second law in the input part, then supplied voltage is VI, that is input voltage, out of which one part you will get across RB, and that part is current into resistance, that is IB into RB. IB into RB, correct? And then remaining voltage you are going to get between base and emitter. Let it be VBE, by symbol VBE, correct? So supplied voltage is equal to summation of voltages obtained. Now in the output part, if you apply Kirchhoff's second law, in the output part, supplied voltage is VCC, out of which one part of the voltage drop you will get across RL, that is current into resistance, which is IC into RL, IC into RL. And remaining part of the voltage you will get between collector and emitter. Let it be shown by symbol VCE, VCE, correct? This is the equation for input part of the circuit. This is the equation for output part of the circuit. Now you can have two possibilities. Either you may supply this input voltage, or you may not supply that input voltage. So suppose I am not supplying any input voltage. So input voltage is 0. Input voltage is either very small or equal to 0. So VI is nearly 0. When there is no input voltage, when there is no forward bias in the input, naturally you will not get any base current. So base current IB is 0. Base current IB is 0. Now for this common emitter mode, don't you know IC equals to beta into IB. IC equals to beta into IB. But when IB is 0, put it here. 0 into beta will be 0. When IC is 0, put it here. Put it here. So you will get VCC equal to VCE. Come on, VCE equal to VCC. Come on, when you put IC equal to 0, VCC equals to VCE, VCC equals to VCE, and what is this VCE? It is nothing but output voltage. So this is nothing but output voltage. So you will get output voltage equal to VCC, and whatever is the EMF of this battery, that is maximum voltage you will get in this output part, correct? Because this battery has got constant EMF equal to VCC. You cannot get voltage more than that out of VCC. You cannot get voltage more than that, correct? So that VCC must be maximum. So what does it imply? When input voltage is 0, output voltage is maximum. When input voltage is 0, output voltage is maximum. So when we are not supplying any voltage in the input, we are getting maximum voltage in the output. And at that time, because collector current is 0, transistor is said to be in a condition called cutoff condition. In which state it is lying? It is lying in a cutoff state. Cutoff state. Whenever collector current is 0, we say transistor is in a cutoff state. Okay, fine. Now let us consider second possibility. Suppose we are supplying that much maximum input voltage which can give you maximum base current. When we supply here forward bias voltage maximum, naturally this base current also will be maximum. But when IB is maximum, put it here. Put it here. When IB is maximum, you know, IC equals to beta into IB. IC equals to beta into IB for common emitter mode. When IB is maximum, IC has to be maximum. So I am writing IC equals to maximum. Whenever collector current in a transistor is maximum, we say transistor is in a typical state called saturation state. What is it called? Saturation state. So in case of saturation state, collector current is maximum. When IC is maximum, put it here. When this IC is maximum, this part would be maximum, and when this part is maximum, this summation has to be constant. But among that summation, this part is maximum, so this part has to be minimum, nearly 0. Nearly 0. When this is maximum, this is minimum, nearly 0. So we say VCE is nearly 0. When VCE is nearly 0, then VCE is nothing but right now output voltage. So output voltage is nearly 0. So when input voltage is maximum, the output voltage is 0. But at that time, transistor is said to be conducting because there is a maximum collector current, and the transistor is said to be in a state called saturation state. Here transistor is in a cutoff condition. Here transistor is in a saturation state. Correct? Now, let us take next article. Very important, bit lengthy, bit interesting also, but very important from examination point of view. Use of transistor as an oscillator. First of all, tell me, in second chapter we had studied about parallel LC circuit, isn't it? And in case of parallel LC circuit, there also we had LC oscillations. We had oscillations of charge. But what was the problem in that circuit? In that circuit, we got damped oscillations, in which amplitude of oscillation was going on decreasing. Now we want to have sustained oscillations, meaning thereby oscillations with constant amplitude. How to get that sustained oscillations? I am showing you. For that, you know what you should do? At the end of each oscillation of the charge in parallel LC circuit, whatever is the decrement in the energy, same increase in energy you must supply. So you must compensate the loss in energy, and that too at the right moment. Okay, fine. Let us see how we can do that using NPN transistor. I am showing you in a common emitter mode. Here is use of NPN transistor as an oscillator in common emitter mode. Collector base emitter. Here we have changed the symbol of collector. Instead of C, we are adding C1 because C is a symbol given to the capacitance of a capacitor. Okay, so we just give different symbol here. C1, collector C1, base B, emitter E. And because it is NPN transistor, I am just writing NPN, correct? And for NPN transistor, you know, arrow is shown on emitter that toe outward, correct? Through VCC, we are supplying necessary reverse voltage, and through VBB, we are supplying necessary forward voltage, okay? Come on, EMF of the battery connected with base, we show it by symbol VBB as per the textbook. EMF of the battery connected with collector is shown by this symbol VCC, correct? Fine. Here in the input section, we have connected one parallel LC circuit. L is the self-inductance of this coil and this C is the capacitance of this variable capacitor. Because it is variable, just we show it symbolically, this arrow. This arrow shows that this capacitance can be changed, okay? Fine. Then here, this collector is connected with another coil having inductance L1 as shown in the diagram. Actually speaking, these two coils are wound on same isolated soft iron cylinder. They are wound on same core, same isolated soft iron cylinder. That's why these two inductors have some sort of coupling between them. Because they are joined through phenomenon called mutual induction, we say there is some inductive coupling between these two coils, okay? Meaning thereby, whenever there is change in magnetic flux linked with this coil, there will be production of induced EMF across this coil, okay? So they are linked with a phenomenon called mutual induction. This sort of coupling, this sort of connection is called inductive coupling, correct? Fine. Now, how does collector current change with time, that I have shown graphically in this diagram, and how does effective forward bias voltage changes with time, that I have shown graphically in this diagram, okay? Let us consider this instance of time 0, T by 4, T by 2, 3T by 4 and capital T. 0, T by 4, T by 2, 3T by 4 and capital T, okay? Fine. Now initially this key is kept open. Initially this key is kept open. And then after what we do, we just close this key. And then after we just keep it closed only. Fine. When you make it closed, naturally, because of this supply, because of this battery, some current will start flowing in the collector part, which we call collector current, okay? Fine. When that collector current is flowing through this inductor, naturally, it will produce its own magnetic flux, fine. So because of current passing through this inductor, it has some magnetic flux. It gets associated with some magnetic flux, fine. And because that current is increasing with time, the magnetic flux linked with this coil also goes on increasing. And because these two coils are inductively coupled, because of increase in magnetic flux here also there is increase in the magnetic flux linked with this coil. And because of change in magnetic flux, here it so happens that some induced EMF gets developed across these two ends of this coil. And it so happens in this case, during the increase of magnetic flux, I have written here, from 0 to T by 4, during the increase of magnetic flux, the upper plate of this capacitor becomes positive because of induced EMF and lower plate becomes negative. Now, if you see the polarity of this potential difference and this potential difference, then you will notice that as if these two batteries are connected in an assisting manner, And because this potential difference assists this EMF, then effective forward bias voltage has been increased. And because VF is increasing, effective forward bias voltage has been increased, then naturally in the input section, if forward bias voltage increases, it would increase base current. So IB will increase. And common emitter mode, you know, collector current IC is beta times IB. When IB is increasing, naturally IC also will be increasing. So IC is increasing. And that is why IC are shown in the diagrams. Look here, it is increasing. And finally at T by 4, it becomes maximum. Fine. Now, once the collector current has become maximum, it is not going to increase further beyond that, correct? It's not going to increase beyond that. So that's why that maximum current is also called saturation current. So transistor has come in a state called saturation state. Okay, fine. Now tell me, from T by 4 to T by 2, what will happen? See, at T by 4 it so happens that collector current has become maximum, further it is not going to increase. So now the current passing through L1 stops changing. When current passing through L1 stops changing, at that time magnetic flux linked with this coil also will stop changing. And because there is no more change in magnetic flux here, it will so happen that whatever magnetic flux it had at time T by 4, that magnetic flux will start decreasing, So magnetic flux linked with this coil decreases. Earlier magnetic flux was increasing, now magnetic flux of this coil goes on decreasing. During the increase of magnetic flux, the polarity of the voltage was this. Now there is opposite polarity. Upper plate becomes negative and lower plate becomes positive for this capacitor. And in that case, this potential difference opposes this EMF. When this potential difference opposes this EMF, then effective forward bias voltage will decrease. When effective forward bias voltage will decrease, in the input part base current will decrease. As base current will decrease, collector current also will decrease. Collector current decreases, and that is how ultimately it becomes 0, correct? Now same cycle is getting repeated. As I explained earlier, it becomes from 0 to maximum, then after it decreases from maximum to 0. Look here, 0 to maximum, maximum to 0. Again repeat it, 0 to maximum, maximum to 0, correct? This is how the value of IC, collector current, increases from 0 to maximum, it decreases from maximum to 0. That is how it keeps on oscillating between two values, 0 and maximum. 0 to maximum, maximum to 0. 0 to maximum, maximum to 0. This is how it is keeping on oscillating. Okay, fine. Now here, so far the charge in this LC circuit is concerned. Suppose you are talking about electron. If electron in the time from 0 to T by 2, they are going this way, then in the remaining equal time they will go this way, correct? So this charge is keeping on oscillating here. Fine. Now here collector current is changing between 0 and maximum. It is oscillating between 0 and maximum, and just opposite to this coil we have kept in the output one more coil, and across which we are going to get output signal voltage, and that output signal has pulses like this. Pulse means half of wave, and in that you will find very high frequency, correct? Depending upon the what frequency you are setting here, depending upon that same frequency you will notice here in the output voltage, and that frequency is given by this formula, 1 upon 2 pi into under root of L into C. F equals to 1 upon 2 pi into under root of L into C. Suppose you are keeping this inductance constant, but if you change this capacitance, then depending upon different values of capacitance, you may have different values of frequency. But normally we use this oscillator circuit to obtain very high frequency, as high as up to 10 raised to 9 hertz, and such high frequency oscillations are very useful in radio and TV transmitters, about which you will study in the next chapter, and in the field of communication also. Okay. And what is the speciality of this circuit? Here we do not require any input signal. Just recall the amplifier circuit. In case of amplifier circuit, we had connected signal voltage source, that was Vs. So that time in the input we require some input AC signal. Here we do not require any input AC signal. Such a circuit is also called positive feedback amplifier. Okay. Now here between this inducing EMF and induced EMF, there is already 180 degree phase difference according to Lenz's law, and in case of common emitter amplifier, you know there is 180 degree phase difference between input and output. So one more 180 degree phase difference is introduced. So totally it will be 180 plus 180, that is 360 degree, or you may say 0 degree. Having phase difference 0 degree or 360 degree means just at the right moment when this circuit requires the energy, you are feeding that energy to that circuit, and that's why the output voltage and input voltage ultimately are in phase. In phase means having phase difference 0 or 360 degree. And because whatever energy is required at whatever time, we are feeding that much energy at that time only, there is no decrease in energy, there is no decrease in amplitude. That's why you are going to get common oscillations with constant amplitude, and that too with very high frequency. Okay, fine. Here this energy stored in this battery in the form of DC is converted into form of AC energy. So DC energy is converted into AC energy using this circuit which is called oscillator. Alright. Now come on my dears, let us see remaining part of this chapter which is very important, called digital electronics. First of all, let us see what is called a logic. What do you mean by a logic? Logic is that meaningful question which has only two guaranteed answers, either yes or no. Any meaningful question which has only two possible answers, either in terms of yes or in terms of no, is called a logic. Will there be any rain tomorrow? Can you say with guarantee yes, or can you say with guarantee no? No. So such question cannot be treated as a logic. But if somebody is asking you, was there any rain yesterday? Then for that you are 100% sure. If rain is there, then also you are 100% sure. If rain was not there yesterday, then also you are 100% sure. So such meaningful question which can have only two possible answers, either yes or no, is only known as a logic. Okay, fine. Now, there was a mathematician, Mr. George Boole, and what he had done, he had formulated one special mathematics. It is called Boolean algebra using the principles of logistics. Using the principles of logistics, this fellow had prepared, he had formulated a branch of mathematics called Boolean algebra. Okay, fine. Then history says that in the year 1938, there was a physicist, Mr. Shannon, and he had prepared some definite electrical circuits. They were acting like a switch. So such definite electrical circuits designed by Mr. Shannon, which act like a switch, are known as logic circuits. What are they called? Logic circuits. Okay, fine. They are called logic circuits. And a branch of physics in which we deal with logic circuits is called digital electronics. A branch of physics or a branch of electronics in which we deal with logic circuits is called digital electronics. It is very useful in the fields like microprocessors, computers, CD players, medical equipments, in the field of communication. It is very useful. Okay, what? Digital electronics. Fine. Then, so far the output voltage is concerned in a logic circuit, it has only two states. Either you will get output voltage or you will not get it. Okay, either output voltage is obtained or it is not obtained. If output voltage is obtained, then we call it one state or on condition of the circuit. Okay, if we do not get output voltage, we will say it is zero state, or it is off condition of a logic circuit. I repeat, if output voltage is obtained, state of the circuit is said to be 1, condition of the circuit is said to be on. If output voltage is not obtained, the state of the circuit is said to be 0, or condition of the circuit is said to be off condition. Okay, fine. Because the output of logic circuit can have only two states, either 0 state or 1 state, we can describe its output by only two numbers. That's why we call such a system as binary system. So using binary system, we can describe the working of any logic circuit. Okay, fine. Then what about use of digital electronics? Just now I told you, in the fields of communication, this TV, remote control, CD player, then in the field of medical equipments, microprocessors, computers, etc. Okay. Let us see what is called analog signal. Analog signal. See, I told you what is called signal. a quantity which keeps on changing with time is called a signal. But if that changing quantity is electrical quantity such as current or voltage, we call it electrical signal. Such electrical signal can have of two types. It can be of two types. First is known as analog signal. See, this is analog signal, in which you can notice in the figure, it changes continuously with time. It changes continuously with time. Then its value can be anywhere between minimum and maximum. Its value can be anywhere between minimum and maximum. Fine. Here it is also analog signal. It is also changing continuously with time, and it is changing here randomly, irregularly, and here it changes periodically. Okay, but both of them are analog signals. What about second type of signal? We call it digital signal. Just look here in the figure carefully. In case of digital signal, the shape is like this. What does it mean? That for certain time interval, voltage level is minimum, we say 0 level. For certain other time interval, voltage level is maximum, we say level is 1. Then 0, 1, 0. For whatever is this time interval, double than that is this time interval, so I am writing 1 2 times. And same time interval is here also, here I am writing 0 0 2 times because it is low level. Okay. So in such signal, the value of voltage is either minimum or maximum. It cannot have third value. Come on, either minimum, that is 0, or maximum, that is 1. It cannot have third value. Okay. And such signals are called digital signals. Here in case of digital electronics, all the batteries supplied in the input, we will have EMF 5 volt only. So in the output, maximum 5 volt we are going to obtain, maximum 5 volt. Okay. And that will be called as state 1, and if no voltage is obtained, then we say state is 0, correct? If in the output we get 5 voltage, 5 volt voltage, then we say state is 1. In the output we do not get any voltage or minimum voltage, we say state is 0, correct? Fine. This minimum voltage may be 0, may not be 0, but it is minimum, that is sure. Okay. If it is not minimum, then it is maximum because it is digital signal. Okay, it cannot have third value, either minimum or maximum, that's all. Now we go for logic, what is called logic gate. What is called logic gate? Fine. Any logic circuit in which number of inputs is either 1 or more than 1, but output is only 1, is called logic gate. A logic circuit having input either 1 or more than 1, but output is only 1, is called logic gate. Fine. We have two types of logic gates. One is called fundamental, basic, another is called universal. Let us see which are fundamental or basic logic gates. They are three: OR gate, AND gate, NOT gate. Come on, basic are, come on, OR gate, AND gate, and NOT gate. Why the name is like this, I will show you. And universal gates are NOR gate and NAND gate. NOR gate and NAND gate, they are called universal gates. Why do we call these gates as universal gates? There is a reason behind that. Using this NOR gate or NAND gate, in this chapter we will study in the numericals. Using this NOR gate or NAND gate, you can prepare all three basic gates. So that sort of logic gate using which we can prepare all the basic gates is said to be universal. Is said to be universal. Universal gates are only two: NOR gate and NAND gate. Got it? Fine. What is called Boolean equation? Boolean equation. A mathematical equation which describes the working of a logic gate mathematically is known as Boolean equation. An equation which describes working of a given logic gate mathematically is known as Boolean equation. Okay. What about truth table? Truth table. A table which shows the possible combinations of inputs and corresponding output mathematically is known as truth table. A table which shows possible combinations of inputs and corresponding output mathematically in the form of a table is called a truth table. Okay. Let us see now all the three basic gates one by one. Firstly, we will discuss about OR gate, then AND gate, and then after NOT gate. Let us see one by one. Number one, come on, OR gate. Why the name is like this, you will understand. Consider the circuit diagram or the logic circuit as shown in the diagram. What do you notice in the logic gate? Logic circuit. What do you notice? How it is a circuit? Very simple. There is a parallel combination of two switches A and B connected with battery and bulb. Parallel combination of two switches A and B connected with battery and bulb as shown in the diagram. Okay. Now tell me, how many inputs are there? Two. One is A, another is B. Remember, if there are n number of inputs, then number of possible combinations of inputs is 2 raised to n. Right now n is 2, so 2 raised to n is 2, so 2 raised to 2, that is 4. So you can have 4 possible combinations with these two switches. Which 4 possible combinations I am showing you? Either you can keep both the switches open, correct, that is the first possibility, or in the second possibility you may take first switch open, second switch close. In the third you may take first switch close and second switch open, and in the fourth possibility you may take both the switches close. Okay, that is how you will have maximum 4 possible combinations, not more than that. Come on, open open, open close, close open, close close, correct. Here I am writing for A, here I am writing for B. Output of any logic gate is shown by symbol capital Y, and how is the output in this case I am showing you. Naturally, when you keep both the switches open, no current will pass through any switch, and if no current passes through any switch, naturally no current will pass through bulb. If there is no current in the bulb, naturally bulb will remain off, correct. Come on, open means you are not supplying any voltage in the input, then it is 0. Come on, open means 0, and here bulb is remaining off because you are not getting any voltage across the output. That's why output condition is shown by symbol 0. So here state is 0, here state is 0, here also state is 0. Now tell me, if you keep this switch open and if this switch is closed, then when this switch is closed, then what will happen? Current will pass through this switch and that current will pass through the bulb, correct. When bulb it carries some current, when bulb is conducting some current, naturally it will glow. So condition of bulb becomes on condition, correct. On condition means state is 1. When this switch is closed and this switch is open, close and open. Because this switch is closed, come on, current will pass through this switch now, correct. And that current will definitely pass through bulb. When current passes through bulb, it glows, it becomes on. So I am writing on condition. On condition means number 1, correct, state is 1. And if both the switches are made close, then naturally current will pass through both the switches and that total current will pass through bulb. So bulb will start glowing, bulb will become on. So I am writing here on. On condition means state is 1, correct. Now tell me, here for bulb to remain on, correct, you can notice in this table either of these two switches is closed or both of them are made close, then you will get bulb condition on, correct. So either of two inputs or both the inputs are 1, then output is 1. Repeat, either of two inputs or both the inputs are 1, then output is 1. I am writing here, any one input or all inputs are 1, then output is 1. Any one input or all inputs are 1, then output is 1. Any one input, either this or both of them are 1, then output is 1, correct. When both the inputs are 0, then only output is 0, correct. I repeat the working of this gate. Come on, when any one input or all the inputs are 1, then output is 1. So I am writing here any one input or OR. That's why this name of this gate is OR gate. What is it called? OR gate. When input A or input B or both of them are 1, then output is 1. That's why this gate is called OR gate. Simple. This becomes now truth table for OR gate. 0 0 0 1 1 0 1 1, and here you can just write as if you are making the addition of two inputs, as if, actually not addition, but as if you are making addition. And remember, output will never be greater than 1. Output will never be greater than 1. Simply make the addition, then you can write the output very easily. 0 plus 0 0, 0 plus 1 1, 1 plus 0 1, 1 plus 1. Don't write 2, write only 1. As I said, output is not going to be more than 1. Got it? Fine. Now tell me, this becomes the truth table for this OR gate, because you are making the as if, addition of two inputs. As if addition of two inputs, we just put mathematically this way, y is equal to A plus B. But while pronouncing, while speaking, you don't have to speak plus, you have to speak OR. You will always speak out this mathematical equation this way, y is equal to A or B. Y is equal to A or B, correct? And this very equation becomes, come on, Boolean equation. An equation which describes working of a given logic gate mathematically is called Boolean equation. So this becomes Boolean equation for OR gate. What is that? Y is equal to A plus B. While writing, while speaking, y is equal to A or B. Got it? Fine. And this plus sign is called OR operator. Plus sign is called OR operator. Okay, fine. Now tell me, the circuit symbol for OR gate is this. Don't make any change. There are three curves. One is this, another is this, third is this. Correct? These are the two inputs, and this is output. Okay? Y is equal to A or B. Y is equal to A or B. This is the circuit symbol for OR gate. Fine. Let us see about AND gate now. What is called an AND gate? Why the name is like that? You will come to know. Consider the logic circuit as shown in the diagram, in which there are two switches A and B connected in series with one bulb and one battery. Fine. Now because there are two inputs A and B, only two inputs, then how many possible combinations? 2 raised to n. So 2 raised to 2, that is 4. Come on, for A I am writing here, for B I am writing here. Which are the possible combinations? Come on. Open, 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 close, close, open, close, close. Open, 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 close, close, open, close, close. Correct? Open means 0 and close means 1. Open means 0, close means 1. Okay? What about output? We just show it by symbol capital Y. First of all, tell me, when both the switches are open, both the switches are open, naturally no current will pass. When no current will pass through this bulb, bulb will not glow. Bulb will not glow. And when bulb does not glow, bulb remains off. So I am writing here off. The state is 0. When one switch is open, another switch is closed, then also because the whole circuit is not made close, from here it is lying open, no current will pass through this bulb, no current through the bulb, bulb will remain off, that is state is 0. State is 0. When this switch is closed, but this switch is open, close, open, at that time also no current will pass through this bulb, and that's why bulb will remain off, that is state is 0. And now when both the switches are made close, then the states are 1 1, and at that time, because both the switches are closed, current will definitely pass through this closed circuit, and when current is passing through the bulb, bulb will become on, that is its state is 1. So how would you describe this? As if you are making addition of these two inputs. Come on, not addition, I am mistaken, multiplication. You are making as if multiplication of these two inputs. Come on, 0 into 0, 0, 0 into 1, 0, 1 into 0, 0, 1 into 1, that is 1. Correct? Because we are making the multiplication of two inputs, as if multiplication is made, we just put here symbol of multiplication, that is dot. But you should write this way, y is equal to A dot B. But while pronouncing, while speaking, you must not speak dot. You should say Y is equal to A and B. Y is equal to A and B. Why we speak AND? Because in order to have output voltage, we require switch A and switch B. Switch A and switch B, both of them in one state, then only output is 1. When all the inputs are 1, then only output is 1. I repeat, when all the inputs are 1, then only output is 1. Look here, if all inputs are 1, then only output is 1. When switch A and switch B, both of them are closed or both of them lie in state 1, then only output is 1. When input A and input B is 1, then output is 1. Last time, when input A and input B are 1, then only output is 1. Because we are speaking the word AND, we say this gate is AND gate, okay? And because we are just, as if we are taking multiplication here, we just put the symbol for multiplication, that is dot, but actually you should remember AND, the word is AND. You should say Y is equal to A and B, got it? And this dot gives you AND operator. This dot gives you AND operator, okay? The way here plus sign indicates OR operator, here dot sign indicates AND operator. What is the circuit symbol for AND operator? For AND operator, this is the circuit symbol in which here there are 3 line segments and here this part is curved. Fine. There are 2 inputs and 1 is output, and that output is shown mathematically by this Boolean equation, Y is equal to A and B. Boolean equation for OR gate, Y is equal to A or B. Boolean equation for AND gate, Y is equal to A and B. Got it? Now we go for third gate. Third gate is described here. It is called NOT gate. What is it called? NOT gate. Why the word is like that, you will come to know. Consider circuit, logic circuit in which one battery, one key and one bulb are connected in parallel. Fine. Only one input is there, that is switch A. And if n number of inputs are there, what is the total number of possible combinations? 2 raised to n. Because right now n is 1, 2 raised to 1, that is 2. You can have only 2 options with switch A. Either you can keep it open or you can keep it closed. Suppose I keep this switch A open. Open means 0 and close means 1. Let us see one by one. First of all, open. If you keep this key open, naturally, come on, the total current will pass through bulb. When this key or this switch is open, there will not be any current through the switch, but the current will pass through the bulb. And when current is passing through the bulb, bulb will glow. Bulb will glow. So bulb will become on. When bulb turns on, the state is 1. And now suppose I just keep this key closed. If I keep this switch closed, then what will happen? Here we consider a wire of almost 0 resistance. And here filament of this bulb has some resistance. So when you keep this key closed, at that time you are providing this current a path of 0 resistance. Providing a path of 0 resistance means making the circuit short. So there will be a short circuit and then total current will pass through the switch only this way. Then if total current is passing through the switch only, there won't be any current in the bulb. And when there is no current in the bulb, bulb will not glow, bulb will remain off. Off means which state? 0 state. So what have you noticed here? When input is 0, output is 1. Speak reverse. When input is 1, output is 0. So what is output? Negative of input. Negative of input. And mathematically we write this way. Y is equal to not A. How will you pronounce? Y is equal to not A. This line segment, small bar sign, it gives you not operator. The way this plus sign gives you OR operator, the way this dot symbol gives you AND operator, similarly this bar symbol gives you not operator. Okay? How will you pronounce this Boolean equation? Y is equal to not A. Y is equal to not A. Got it? And this is the symbol for, circuit symbol for NOT gate. How is it? Tell me. First of all, you just put one big arrow like this and then put one empty circle, correct? Rather big in size, empty circle like this, okay? And then you can just put two small dots here. This is input, this is output. If input is A, output is Y is equal to not A. Y is equal to not A. If input is 0, output is 1. When input is 1, output is 0. Because the condition or the state of input is getting inverted by this gate, we call this gate as inverter gate. It always inverts the state of input. If state of input is 0, state of output is 1. If state of input is 1, then state of output is 0. Got it? Because it inverts the state of input, we call it inverter gate. And this is the only gate which has one input. Remaining gates have minimum 2 inputs, and NOT gate is the only gate which has only one input. This is the difference, okay? And I just forgot to mention one thing. When we are taking maximum voltage as state 1 and minimum voltage as state 0, we call it positive logic system. Positive logic system. There is another logic system which is called negative logic system, in which the maximum voltage, state for maximum voltage is taken as 0 and state of minimum voltage is taken as 1. But the negative logic system nowadays it is out of use. It is not used even in the textbook also. In the textbook they have used positive logic system. Okay, fine. My dears, just now we have finished the study of 3 basic gates: OR gate, AND gate and NOT gate. And now we go for 2 more universal gates, NOR gate and NAND gate. Why are they called universal? The reason is that we will see in the illustrations of this chapter that using this universal gate, we can prepare all the 3 remaining basic gates. That's why they are called universal. Okay, fine. Let us see one by one. First of all, we start with NOR gate. How it is prepared? Very simple. The output of OR gate is given in the input of NOT gate, and that gate prepared in this manner is known as NOR gate. It is a combination of OR gate and NOT gate. Output of OR gate is given in the input of NOT gate, and then the logic gate prepared so is called NOR gate. Okay, here it is. This is OR gate, symbol of OR gate, output of which it is, come on, OR operation between these two. So y dash equals to A or B. All intermediate outputs you must show by symbol y dash, y double dash, y triple dash, like that, or y1, y2, y3. And only final output should be given symbol y. And here final output will be NOT operation of this. NOT operation of this means not A or B. Not A or B. Correct? And what is the circuit symbol for NOR gate? Very simple. Simply remove this line segment and this arrow. Just remove and show this empty circle over here. Correct? And when you show this empty circle over here, this will be the symbol for showing NOR gate in the logic gate. NOR gate in the circuit. This is the symbol for NOR gate, which is universal gate. Okay? This is symbol for OR gate, and then when you show this NOT operator, then it becomes a symbol for NOR gate. OR plus NOT equals to NOR. What is the output here? First of all, OR operation between these two, A or B, and then NOT operation. So not A or B. Not A or B. Correct? Fine. Now let us go for preparing truth table for NOR gate. Very simple. 2 inputs are there. So what are the possible total number of possible combinations? 2 raised to n. N is 2. 2 raised to 2, that is 4. Come on, A and B. Come on, speak out all the 4 combinations. 0, 0, 0, 1, 1, 0, 1, 1. Here it is. 0, 0, 0, 1, 1, 0, 1, 1. Correct? Then first of all go for OR operation between these two. Then simple addition. 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1, 1 plus 1, take care, don't write 2, only 1. Correct? Output cannot be greater than 1. Fine. And what about NOT operation? NOT operation of this means if it is 0, you have to write 1. If it is 1, you have to write 0. That's all. Instead of 0, come on, write 1. Instead of 1, 1, 1, you will write 0, 0, 0. Correct? How will you describe the working of this NOR gate? Using this Boolean equation, come on, speak out. Y is equal to not A or B, not A or B, correct? And come on, speak out the working in words. When either of two inputs, or both of them are 1, then output is 0. And when both the inputs are 0, output is 1. I repeat, when either of two inputs is 1 or both the inputs are 1, then output is 0. And when both the inputs are 0, then output is 1. Simple. This is the Boolean equation. Y is equal to not A or B. Right? This is the circuit symbol for NOR gate. Now let us talk about NAND gate. AND plus NOT gives you NAND gate. That is, output of AND gate is to be given in the input of NOT gate, and then the gate prepared so is called NAND gate. AND plus NOT equals to NAND. Come on. Here the intermediate output you will show by symbol Y dash. It is AND operation between these two. So Y dash equals to A and B. And then when it passes through NOT gate, it will just perform NOT operation of this. Come on, when you perform NOT operation on this, the final output will be NOT of this. NOT of this means not A and B. Not A and B. Correct? What about symbol? Remove this line segment, remove this arrow, and just show this empty circle over here. Will become circuit symbol for NAND gate. Come on, this is AND gate, this is NOT gate, combination is called NAND gate. AND plus NOT equals to NAND. What about truth table? For two inputs, 4 possible combinations are 0, 0, 0, 1, 1, 0, 1, 1. Correct? Here it is. 0, 0, 0, 1, 1, 0, 1, 1. Correct? What about intermediate output here? Y dash equals to A and B. Perform AND operation, that is simple multiplication. 0 into 0, 0, 0 into 1, 0, 1 into 0, 0, 1 into 1, that is 1. What about NOT operation? When you perform NOT operation, come on, instead of 0, you will write 1. Instead of 1, you are supposed to write 0. 0, 0, 0, then you can write 1, 1, 1. Instead of 1, you should write 0. Correct? Come on, describe this by Boolean equation. Y is equal to, come on, not A and B. Y is equal to not A and B. Correct? Describe this truth table in words. Very simple. When either of, look here, either of two inputs is 0. Either of two inputs is 0 or both the inputs are 0. Either of two inputs is 0 or both the inputs are 0, then output is 1. And when both the inputs are 1, then output is 0. Correct? Fine. This is how we have studied this NOR and NAND gate. Both of them are called universal gates. OR, AND and NOT, they are 3 basic gates. And this NOR and NAND gate, they are called universal gates. Okay? Now let us go for the last article about IC, primary concept of IC, that is integrated circuit. Okay? Come on. History says that the first ever computer prepared in the whole world had very big size. It was having size of a complete room. It was that much big. I am talking about early time, that is in the year 1960. Later on, with the development of electronics industry, we have reduced the size of all electronic equipments considerably. Then after we had been using, come on, tabletops. At present also we are using them in the offices. You find desktop, correct? Then smaller in size, smaller than this desktop, we have laptops, which are also called notebook computers. Then we have palm top or handheld PC, and then still performing faster and better operation than this handheld PC, we have got tablet PC. And right now there are certain apps which you can install in the mobile phone and you can convert it into mini computer, correct? And this reduction in size in various electronic devices, that process is known as miniaturization. Miniaturization. Right now we have the radio also in the size of as small as like size of a ball pen, correct? This process of reduction of size in all the electronic devices is called miniaturization. and there has been great contribution from IC for this process, miniaturization. Okay, how I'm showing you. I'm talking about time before 50 years from now. Before 50 years from now, we were connecting the necessary electrical components by simple metallic wires. We were connecting components like resistor, capacitor, diode, transistor, etc. They were connected by wires. But then those devices were very large in size, heavy in weight, and it was difficult to handle with them. And so far the connections were concerned, they were not that much reliable. Okay, there were problems of loose connection. Then we had removed all those problems. We had prepared new types of circuits called PCB, printed circuit board, in which different electrical components are placed on a non-conducting two-dimensional board, and then after the connections between them, that is interconnections, were made through metallic strips. But then also the size was reduced no doubt considerably, but then also the devices or those circuit boards remain in 3 dimensions. They were occupying big volume, and we wanted still smaller size, correct? For that, what we had done, we had invented, 2-dimensional devices in which the circuits are 2-dimensional, and such circuits are called IC, that is integrated circuit. And for that, what we do, we just take the size of crystal, this much small, 1 millimeter by 1 millimeter, and by process of engraving, we install diodes, transistors, resistors, small size capacitors inside that chip. And that is how the miniaturization process continued, and now we have very small size of the devices, correct, which is called IC, integrated circuit. The classification of IC is based upon number of logic gates inside. Here are shown different shapes of IC. As per the textbook, I have drawn this figure, but when you prepare remaining part of the chapter, then only you should practice for these figures. Okay, generally such figures are not being asked in the examination. Now we go for classification of IC. It is based upon number of logic gates inside. If number of logic gates is 10 or less than 10, we call it SSI, that is small scale integration, correct? This type of IC contains how many logic gates? 10 or less than 10. If number of logic gates is more than 10 but less than 100, we call that IC as MSI. Which class? MSI means medium scale integration, correct? Then if number of logic gates is 100 or more than 100, but certainly 1000 or less than 1000, then we call it LSI, that is large scale integration. And if number of logic gates is more than 1000, we call it VLSI, very large scale integration, correct? In all the computers, the chips, the ICs used, they are of this class, VLSI, very large scale integration. Got it? There are 3 main types of IC. While manufacturing them, there are only 3 types. First is film circuit, in which we have only these 2 components, resistors and capacitors. Then better than that, we have IC, which is called monolithic integrated circuit, in which along with this resistance and capacitors, we have added 2 more components, they are diodes and transistors, okay? And third one, hybrid integrated circuit, which is actually a combination of these 2, combination of film circuit and monolithic integrated circuit is hybrid integrated circuit, okay, in which there are more than one chips. And what does this monolithic word indicates? Mono is a Greek word, it means one. Lithic also is a Greek word, it means stone. Here stone means we should understand crystal. So we take either silicon or germanium. We take single crystal only, and then after we are preparing this IC, then it is called monolithic integrated circuit, okay. With this, I finish the theoretical part of this chapter. Now we will be going for the remaining illustrations, then MCQ and exercise numericals. Okay, thank you. Come on, my dears. Now the illustrations are such that the figures themselves, they represent the statement. So figures I have drawn. You better just continuously see on the board. You will understand not only the statement, its a solution also you will understand immediately. Okay, you continuously stare on the board, please. Look, in example number 9, we are given two signals A and B. And if they are given, if these are the two inputs of OR gate, then what will be output signal in the OR gate? That is what we have to find out. In short, we have to find out output of OR gate. You know OR operation, A or B means simple addition. Simple addition. Come on. 0 plus 0, 0. 0 plus 1, 1. 1 plus 0, 1. 1 plus 0, 1. 0 plus 1, 1. 0 plus 0, 0. 1 plus 1, 1. 1 plus 1, 1. 0 plus 0, 0. 0 plus 1, 1. Correct? Here 0 level means low level and level 1 means high level. Correct? So this will be the signal in the output of OR gate. That's why I am putting Y equals to A or B. Correct? OR operation means simple addition. Simple. Now in example number 10, they have given two NOT gates connected one after another. Output of first NOT gate is given in the input of second NOT gate. We are asked to find out the signals at point X and Y. If input signal A is like this, correct? Then what are the signals at points X and Y? At point X, let it be Y dash. Because this is NOT gate, it will perform NOT operation on A, so it will give you NOT A. Let us find out. Y dash equals to NOT A. NOT means what? Instead of 0, you should write 1. Instead of 1, you should write 0. Come on, instead of 0, 1. 1, 1. In place of that, 0, 0. In place of 0, 1. 1. In place of that, 0. 0, 0, 0, 0. Right? 1, 1, 1, 1. In place of 1, come on, 0. In place of 0, come on, 1. Correct? So this will be the signal at point X. And what will be signal at point Y? Come on. At point Y, suppose output is capital Y, which will perform NOT operation again because it is a NOT gate. And NOT operation when performed on this will give you NOT A. NOT will cancel, giving you A. A means what? Original signal. Correct? You can just verify. Come on. Instead of 1, I should write now 0. Correct? Instead of 0, 0, come on, 1, 1. Instead of 1, I should write 0. Instead of 0, I should write 1. Instead of 1, 1, 1, 1, I should write 0, 0, 0, 0. Instead of 0, come on 1. Instead of 1, come on 0. Correct? And now compare this signal with this signal. You will find same. These two signals are same, identical. This is input signal A and this is final output signal. They are identical. They are same. Correct? Two NOT operations will cancel the effect of each other, giving you original signal. Correct? Fine. Now in example number 11, they have given this sort of logic gate. And we are asked to prepare truth table for this logic gate. Come on. This input is connected with this input of OR gate. So accordingly, we have to prepare the truth table. Because there are two inputs, come on. For two inputs, how many number of possible combinations? 4. 0, 0, 0, 1, 1, 0, 1, 1. The same thing I am writing here. 0, 0, 0, 1, 1, 0, 1, 1. Come on. First of all, this is AND gate. It will perform AND operation on these two inputs. So AND operation means simple multiplication. 0 into 0, 0, 0 into 1, 0, 1 into 0, 0, 1 into 1, that is 1. And what about final output here? This is OR gate. So it will perform OR operation on these two. Come on, this is signal A and this is, come on, output is Y dash. And that Y dash and this A, now you are supplying in the input of OR gate. So this will perform OR operation on Y dash and A. Come on, Y equals to A or Y dash, A or Y dash. Because this is OR gate, I should write OR operation, that is A or Y dash. Come on, Y equals to A or Y dash. This is A, this is y dash, and you are looking for OR operation. OR operation means simple addition. Simple addition. 0 plus 0, 0, 0 plus 0, 0, 1 plus 0, 1, 1 plus 1, that is 1. Correct? So this is the final output of this present logic gate. Okay? Then in sum number 12, we are given one NAND gate whose two inputs are shorted. Making two inputs shorted means connecting them with each other. Okay, there should be interconnection between two inputs, then it is said to be shorted. Okay, then we are asked to prove that it behaves like a NOT gate. It behaves like a NOT gate. Let us prove. Come on. Here is input A, and come on, it is connected here. So here also it is A. And because these two are interconnected, second input as such we give symbol B, but it is same as A because they are interconnected. So B is also equal to A. Come on, for one input, how many possible combinations? 2. I mean, two values of one input. Come on, either it should be 0 or it should be 1 because we are supplying digital signal. Come on, B is also same as A. So here also 0 and 1, here also 0 and 1. What about this gate? This is AND gate, so it will perform AND operation. Means simple multiplication. 0 into 0, 0, 1 into 1, that is 1. Then this empty circle indicates NOT operation. Perform NOT operation on this. So NOT of A and A. NOT of 0 means 1, NOT of 1 means 0. And if you perform NOT operation on this input A, then instead of 0 you may write 1, instead of 1 you may write 0. Now these last two columns you can see here, these last two columns are same. When these last two columns are same, meaning thereby this is the output of this gate and this is the output of NOT gate. So this present gate behaves like a NOT gate, behaves like a NOT gate. So we have proved it. When two inputs of any NAND gate are shorted, it will act like NOT gate. Similarly, let us see one extra sum now. Instead of NAND gate, if you take NOR gate, and if you make two inputs of that NOR gate also shorted, it also will act like a NOT gate. That is what we have to prove. Come on. This first two columns as it is, here it was AND gate, so we had performed AND operation. But this is now OR gate, so we should perform OR operation. OR operation means simple addition of these two columns. 0 plus 0, 0, 1 plus 1, that is 1. And what about this empty circle indicates, come on, NOT operation. Perform NOT operation on this. Instead of 0, you should write 1. Instead of 1, you should write 0. And what about if you perform NOT operation on this A? Instead of 0, you may write 1. Instead of 1, I should write 0. Now you can see these last two columns are same. This is the output of present gate and this is the output of NOT gate. Because last two columns are same, present gate behaves like NOT gate. In short, for every universal gate, you know how many universal gates? 2, NOR and NAND. If you make two inputs of any universal gate shorted, it will act like NOT gate. We have proved. Okay, fine. Now in example number 13, they have shown one logic gate in which 3 NAND gates are connected as per the diagram. 3 NAND gates are connected and we have to prove it acts like OR gate. Let us prove. Come on, two inputs are A and B. For two inputs A and B, how many possible combinations? 4. 0, 0, 0, 1, 1, 0, 1, 1. Correct? Then first of all, because these two inputs are shorted, this will act like NOT gate. So NOT of A I am writing here. Instead of 0, 0, I should write 1, 1. Instead of 1, 1, I should write 0, 0. NOT B I am writing here, that is Y2. And it is NOT operation of B, meaning thereby instead of 0, 1, I should write 1, 0. Instead of 0, 1, again I should write 1, 0. Now tell me, Y1 and Y2. Y1 and Y2. Why I am making AND operation? Because these two, this is Y1, this is Y2. These two are given in the inputs of this AND gate. AND gate will perform AND operation, means y1 and y2. y1 and y2 means what? Multiplication of these two columns, correct? 1 into 1 is 1, 1 into 0 is 0, 0 into 1 is 0, 0 into 0 is 0, correct? And what about its NOT operation? Because this empty circle indicates you NOT operation. NOT operation over this, come on, instead of 1, I should write 0, instead of 0, 0, 0, I should write 1, 1, 1, correct? And then suppose I want to have OR gate, then I should perform OR operation on these two inputs. OR operation means simple addition, 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1, 1 plus 1, that is 1, correct? Now these last two columns you can see, they are same, and this is the output of present gate and this is the output of OR gate. Because these last two columns are same, we can say present gate behaves like OR gate. Fine. Now let us see one extra sum. Look, instead of NAND gate, in the same diagram, identically I have shown at all places NOR gates. If you connect three NOR gates as per the diagram, then we have to prove it acts like AND gate. How to prove? Same way. This first four columns as it is, no change whatsoever. But now this is, come on, OR gate. Output of this is y1, output of this is y2. Because this will, these two inputs are sorted, so this will act like NOT gate, and so output will be NOT of this, that is not A. Here output will be NOT of this, that is not B. Fine. And now this is OR gate, so it will perform OR operation on these two inputs y1 and y2. OR operation means simple addition, so y1 or y2, correct? Come on, simple addition of these two columns, 1 plus 1, 1, 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 0 is 0. And now, because this empty circle is there, it indicates NOT operation, perform NOT operation on this column. Come on, NOT of this means instead of 1, 1, 1, we should write 0, 0, 0. Instead of 0, we should write 1. And if I perform AND operation on these first two inputs, then AND operation means simple multiplication, 0 into 0, 0, 0 into 1, 0, 1 into 0, 0, 1 into 1, that is 1, correct? And now tell me, this is the output of present gate and this is the output of AND gate. And because these last two columns are same, we can say present gate behaves like AND gate. Okay, fine. And now, just one extra information for your kind knowledge. It is not there in the textbook. There was a mathematician, Mr. D. Morgan, and this fellow, Mr. D. Morgan, had obtained two theorems which are very important. And if you utilize these two theorems, then without drawing this diagram, without preparing this truth table, you can just give the final answer directly and correctly. I am showing you how. First theorem is this: NOT A and NOT B is as good as NOT of A or B. NOT A and NOT B is equal to NOT A or B. NOT A or NOT B is equal to NOT A and B. Just see the change. Instead of dot, you are supposed to write plus. Instead of two small bar signs, you are supposed to write one bigger bar sign. Okay. So when you just increase the size of bar from two small, if you just show one long bar sign, then instead of plus, you should write dot. Instead of dot, you should write plus. That is how you can remember. Correct? I repeat, not A and not B is equal to not of A or B. And then not A or not B is equal to not of A and B, correct? Not of A and B, correct? Now, how to get this final output? Very shortly, using this De Morgan's theorem, I am showing you. Come on. What is the output of this? Y equals to not y1 and y2. Not y1 and y2. But what is y1? Y1 is what? Not A. Y1 is not A. Y2 is not B. Now, use De Morgan's first theorem. Come on, this not as it is, but not A and not B, it is as good as not A or B, not A or B, and not will cancel, giving you A or B, correct? So this acts like a OR gate. Now for extra example of 13, for this 13 example, this is extra, and for this we have to prove that it acts like an AND gate. Let us prove. Come on, what is the output here? Y equals to not y1 or y2. Not y1 or y2. This not as it is. But what is y1? Y1 is not A, y2 is not B. Y1 is not A, y2 is not B. Now this outside not sign as it is, and inside you can use De Morgan's second theorem, not A or not B is equal to not A and B. Come on, not A or not B is equal to not A and B, correct? Not will cancel, giving you A and B. A and B means what? It acts like AND gate, okay? So please remember them, these two De Morgan theorem. It will be very useful to you in the MCQs and later on in the examples of exercise. Got it?